This is the fifth and final session of the Logistic Regression series. In this video, we will learn about the Locally Weighted Logistic Regression, LWLR. Let's take a look at the weighted objective function and implement LWLR in code. This video was produced in Korean and translated into English. My voice was generated using AI, text-to-speech. Let's take an overview of LWLR and look at the weights and objective function. And we will implement LWLR using SciPy and Scikit-Learn. Let's apply LWLR to a dataset containing single and multiple features. Then we check the nonlinear decision boundary. The concept of LWLR is very similar to Locally Weighted Linear Regression, LWR. LWR can produce a nonlinear regression curve. And LWLR can also produce a nonlinear decision boundary. In this linear regression video, we looked at Locally Weighted Regression, LWR. We saw that the regression curve was generated like this. When classifying these data points, LWLR can create a nonlinear decision boundary like this. Let's look at the data below. There are several training data points and two test data points, TX1 and TX2. The training data points at the bottom have class 0, and the training data points at the top have class 1. The test data point on the left can be predicted using a sigmoid 1 curve. And the test data point on the right can be predicted using a sigmoid 2 curve. It appears that two sigmoid curves are needed to classify this data. This will give us two decision boundaries. There are 2 points where the sigmoid function has a value of 0.5. So we have two decision boundaries like this. The data points outside these decision boundaries are classified as 0. And the data points inside these decision boundaries are classified as 1. Implementing this approach requires assigning a weight to each data point. Calculate the weight of each data point using a normal distribution. This is exactly the same as locally weighted linear regression. When the test data point is on the left, the weight of the training data on the left is high. And the weight of the training data on the right is small. So the logistic regression is performed primarily using the data points on the left. If the test data point is on the right, the training data points on the right will have high weights. The training data points on the left have small weights. So the logistic regression is performed primarily using the data points on the right. This creates two sigmoid curves like this. This is also a lazy learner like LWR or KNN. Let's look at the weights and objective function. The normal distribution is often used as a weight or kernel function. Measure the distance between the test and training data point. The distance can be a one-dimensional or a high-dimensional. And the PDF value of the normal distribution for this distance is used as the weight. Here, tau is the standard deviation. If the distance is close to 0, the weight is close to 1, and if the distance is far, the weight is close to 0. The closer the training data point is to the test data point, the greater the weight, and vice versa. The The standard deviation tau can be used to control the range of neighbors. This is a hyperparameter. Small tau narrow the range of neighbors, while large tau expand the range of neighbors. If we apply weights to the existing objective function, this is the objective function for LWLR. Now let's implement LWLR using SciPy's optimize class. Create a simple dataset. The data looks like this. The number of features is 1, and the target Y is binary data with 0 and 1. The data points at the top have Y equal to 1, and the data points at the bottom have Y equal to 0. We generate 2,000 pieces of this data. Then we split it into training and test data. Add a column vector where all values are 1. Let's check this data visually. The results are like this. Next, we will write a function to calculate the weights of the training data. XX is the training data points and TX is the test data point. Tau is the standard deviation of a normal distribution. Calculate the distance between test data and training data. Then calculate the weights of the training data points. Next, we will write a function to calculate the loss function. The loss function is a weighted binary cross-entropy. Calculate the y-hat of the training data points using the logistic or sigmoid function. Here the capital W refers to the model parameters WB, not the weights. Then we use y-hat to calculate the binary cross-entropy. The loss function is as follows. This part is the binary cross-entropy. Just multiply this by the weights. Then calculate the average of the weighted binary cross-entropy. Next, we predict the classes of the test data one by one. The test data is read one by one to calculate the weights of the training data points. We then use SciPy's optimize.minimize function to minimize the loss function defined above. The initial values of parameters b and w are each set to 0.1. Then we pass in the weights calculated above. The optimal parameters are contained in the result.x variable. This is used to predict the classes of the test data. This is the yprob. Next, we visualize the training data, test data, and predicted probabilities. And measure the accuracy of the test data. If the predicted probability is greater than 0.5, the class is predicted as 1, otherwise it is predicted as 0. This is the ypred. And we use the predicted class and the actual class to measure the accuracy. Let's check the results. The accuracy of the test data is measured to be 0.98. And the visualization results are like this. If the test data point is at this location, the predicted probability is about 0.1. So we predict the class Y as 0. If the test data point is at this location, the predicted probability is about 0.8, so we predict the class Y as 1. If the test data point is at this location, the predicted probability is about 0.2, so we predict the class Y as 0. You can see that two sigmoid functions are created like this. And you can see that two decision boundaries are also created. All data points outside the decision boundary are predicted to be 0. And all data points inside the decision boundary are predicted to be 1. Let's run this code. The results came out like this. This time we will implement LWLR using Scikit-Learn. Let's use the same data as the previous code. The function for calculating weights is also the same. The test data is read one by one to calculate the weights of the training data points. Create a logistic regression model. Then we fit this model to the training data. Pass the weights calculated above to the sample weight argument. Then calculate the predicted probability of the test data. The rest of the code is the same as the previous code. The accuracy of the test data is measured to be 0.965. And the visualization results are similar to the previous code. Let's run this code as well. The results came out like this. Next, let's implement LWLR for multivariable data. Create a simple dataset. The data is like this. Red data points have class 0 and blue data points have class 1. There are two features, x1 and x2. Visualize the distribution of the data. The results are like this. Split this data into the training and test data. Then we write a function to calculate the weights. Next, we predict the classes of the test data one by one. Read the test data one by one and calculate the weights of the training data points. Same as the previous code, we create a logistic regression model and fit it to the training data. Use the weights calculated above, and then predict the classes of the test data. Measures the accuracy of test data, and visualize nonlinear decision boundary. The code below is identical to the one implemented in the second video. Let's check the results. The accuracy is measured to be 0.92. And the nonlinear decision boundary looks like this. You can see that it classifies the blue and red data clusters well. The standard deviation tau was set to 1.0. Let's run this code. The results came out like this. Lastly, let's see how the decision boundary changes when the standard deviation tau changes. The decision boundary when the tau is 0.1 is like this. The decision boundary is so detailed that there is a possibility of overfitting. If you increase the tau slightly, you will see that the decision boundary becomes slightly smoother. And if you increase it more, you will see that it becomes flat like this. Setting the tau very large results in a decision boundary that is close to a straight line. This may result in underfitting. Let's change the tau to 0.1 in this code and run it. You can see the detailed decision boundary like this. So far, we have looked at logistic regression through a total of 5 videos.